All right. Hi, everyone. I'm Jerry Angelatis from BBN. I'm filling in for Hakan Terechi to moderate the session. And I'm very excited that, we're all here bright and early for this thrilling session on analog quantum simulation across platforms. We've got a great slate of speakers, starting with Pedram Roshan from Google. Take it away.
Thank you. Good morning, everyone. Is this on? Is it functional? Okay, all good. Yeah, anyways, let me get this started by obligatory Feynman quotation, so our next speakers don't need to repeat this. Well, someone had to do it. And I'm not going to read it for you because I'm sure from you have seen it many, many times and you know it by heart by now. But if I have to give it my own reading of what it means if it was written for the this year or now, for 40 years after he has written the original paper, I would say it's about many-body physics and doing many-body physics on quantum processors. So I would not talk much about the quantum processor aspect of it. I think it would be covered maybe by other speakers, or we can assume you already know about it. But what I can only say that, we have an array of nonlinear resonators. You can see a picture which is about a decade old, about 8 nonlinear resonators, which we call them qubits, and there are 9 qubits and 8 coupling between them, and there would be a readout mechanism, and they are all controlled, and we are coloring them so you know the functionality of each element. So this is the working horse. This is the hardware part, but the many-body part. The many-body problem is about, to me, is about a study mainly non-equilibrium dynamics in spin models. That's the many-body physics that is close to us, given the hardwares that we have these years. So this plot has been made several years ago, but it's such a rough estimate of things that hardly can be falsified because it just doesn't have that much information in it. Well, what it says that if you have a few qubits, maybe about a few tens of qubits, but you have a really, really good control of them, really good high fidelity control of them. The vertical axis is getting exponentially harder to control the number of qubits. Then the problems in spin models and problems in maybe even fermionic chemistry land would come to your horizon, and this is what you could do. And I would be talking about the things that we have done mainly after the beyond classical experiment of 2019. So as you might know, the Google Quantum AI main effort is toward making a large fault-tolerant quantum computer. And that is not the subject of this talk. There's lots of other talks about that. But my focus would be on how to advance this NISQ agenda, or how to do NISQ algorithms. And our way of doing it is by choosing and defining a project. And here you can see some of the projects that we finished since 2019, 2020. And I'm sure your time is far more valuable than listening to me going over all of this. So I chose 2 of them, and I would go over the detail of them, and I explain to you how these works are done. Basically, usually there is some hardware development, usually some gate fidelity improvement, some measurement breakthrough or something, or someone can think about a clever architecture or how to lay out the hardware. I think is going to be the focus of Alicia's talks. And usually there is an algorithm development. Someone figures out how to simplify an abstract algorithm such that it's doable and feasible for us to do in the lab. Or someone figure out how to mitigate errors in the theory, and then the idea is to put this together. The focus of error mitigation, I think it would be something that Zlatko would be talking toward the end of the session. And you put these 2 elements together, And what comes out of it is something which I call it discover. This is a word I just made last night, so don't look it up. It doesn't exist. And here's here is a little more better definition of it. That you come at something that a theorist wouldn't know before that, okay? So you put all these bells and whistles together, you make a hot air balloon in this analogy, and you're going to discover a land which a theorist wouldn't know before that. But as soon as you discover it, people figure out many other ways to get there. So it hasn't been the most optimal way of getting there, but it's been a possible way to get there, and you got there first. The point is that you have a very complicated device, and you get there, and you say something a theorist know before them. This is the definition of discovery captured by this figure, okay? But people figure out, oh, they could have walked to this new land anyways at the end of it, but that's besides the point. So without further ado, let me just get to the first experiment I'm about to talk. This work was published in Nature about 2 years ago. Some of my colleagues at Google really focus on this work, but is the whole work done, of course, relied on Google infrastructure. And is about formation of bound states of microwave photons. So the Hamiltonian, the starting point of the discussion is Heisenberg or XXZ chain. This is known since maybe a century ago. And this Hamiltonian, delta, if delta is 1, this is the anisotropy parameter. If it's 1, then you have you have Heisenberg. If it's deviate from 1, you have XXZ chain. The working horse in the lab to realize the dynamic under this Hamiltonian is the FSIM gate, which we introduced a few years ago. And it has two terms. We can forget about the beta for the time being. It can really do the same dynamic as you expect in the Heisenberg Hamiltonian. And we have a very good calibration of these FSIM gates. And after we get a hold of it, we put them in this staggered pattern, and we realize a Floquet dynamic. In the limit that these theta and phi are very small, we realize there is a Trotter realization of the Heisenberg model. But we are not going to be confined to this limit. Theta and phi could be much larger than 0, can be finite size. But the dynamic is the same. So the many physics follows from the symmetries and the interplay of these two factors, so it follows the same. In particular, we are going to focus in the bound state formation. The fact that this Hamiltonian is integrable and beta ansatz comes from there is about, as I said, about a century old. And about 10 years ago, it was shown that this model can host, the formula rather, for bound state has been written for it, and has been realized a year later as the analytics was written by a group of Emanuel Bloch. So basically, they showed that there is indeed bound state formation in this model. What does it mean? It means that if you have a chain of spins and you flip two spins next to each other, you form a magnon. The propagation of them would follow, and they would be together at all time. You take a snapshot of it at any instance of time. They have diffused and they have moved around, but they are going to be together. You're going to be always finding them to be together. And this is the physics that we are going to follow in here. And there has been analytical work by Tomasz Prosen and Igor Aliner from our team who are showing that indeed the Floquet version of it, when your theta and phi are not necessarily small, follows the same physics. There is a bound state and up to all orders. Okay. So here what we are going to do, we are going to get a chain of 24 qubits, and we're going to put them in 1D ring. And we are going to excite a couple of qubits next to each other. And we are going to take a snapshots of this evolution under the unitary I just mentioned many, many times. No, I'm happy.
Oh, you're good? Okay.
Yeah.
I didn't see it.
Yeah. So we're going to take these snapshots, and we see what kind of bit strings we find. Starting, of course, with one excitation. So there is nothing for that excitation to bound with. This excitation is happily jumping around and has its own it's not called catwalking, it's something else, but anyways. It has it diffuses, it has its own random walk on this lattice on this 1D ring, and it interferes and whatnot, and this is a non-interacting picture that you got. That's great. But now you put two excitations, and you say, where did the bit string goes, and take a you evolve it for 1 cycle, 2 cycle, you stop it, you take maybe 10,000 bit string, it takes a second to get 10,000 bit string, and you show where you found the photons. And you can see there is a propagation seems to be slowing down compared to the original one. And you go further and further with putting few more excitation next to each other, and you can see that indeed there is very much a concentration of this intensity or color as you find the bit strings showing that they are indeed seems to be close to origin. So this is a little weak, I would say, evidence that they are forming a bound state. That means they are getting sluggish and they don't propagate faster and they stuck together. A little better evidence comes from further analysis of the same data. Here, I'm going to separate the bit strings we got into two groups. One group is the ones that we find the excitations to be next to each other. I call them T together. And then there are all sorts of other bit strings, which are exponentially many, that the excitations are not next to each other, separated. And let's just look at these T-bit strings and represent them with the center of mass where they are. And you can see that as we do this analysis, or the same data analyzed differently, you can see that the two excitations show exactly the same interference pattern that the single one was showing, meaning that these two are happily staying together and doing the exact same interference that was single. They behave essentially as a single excitation with the propagation velocity just as smaller. And the same going all the way to 5 excitation, the propagation velocity just gets very, very much smaller. You can look at the propagation velocity, and it follows the prediction of the analytical prediction we had. And also you can look at the decay. So this is showing that there is a dephasing in the post-selecting on the energy loss, photon loss, but we cannot fix the dephasing, and dephasing leads to decay of this parameter. This parameter is how often they are together. In the absence of dephasing or in the pure unitary evolution, these lines should have been flat. They are not, meaning that the system is effectively have some open physics to it. Okay, so now I want to get to momentum space picture. That was the real space picture. In the momentum, there is a few body spectroscopy technique that we came up with, and essentially is measuring the green function of the system, which is measuring the lowering operator of qubits. And this is only few body physics because it's not going to be scalable. As you can see, when you make the product of these Pauli operators, the number of excitations you make become important. So if you have 5 excitations to begin with, you have to measure 32 Pauli terms. And this is non-Hermitian, and the way to make a non-Hermitian measurement is by just making pieces and then adding up pieces. So that's how it's constructed. So you measure the expectation value of these lowering operator by piecewise measuring them. And you do as a function of space and time, and it looks like absolutely nothing. When you do Fourier transform, 2D Fourier transform, then you can see a really nice band forming similar to tight binding that you're familiar with. It's slightly different from that, but it's very similar. As I said, you can push this idea maybe up to 5 excitations, and you can see the bands are forming, and we can resolve the bands of the bound states, and the band is getting flat, getting more flat, showing that the dominance of interaction over the kinetic term in these as you put more excitations. As I said, there's the dashed lines are the analytics for it, is not your energy being cosine of k, is cosine inverse of cosine of k. So it's a little more complicated because of the flaquette I mentioned, but overall there is a good control from it. From the analytics that Igor Alainer worked out. So as soon as you want to kick back and watch some commercials and be done with it, you get this news that, okay, look, what was the original physics of it? The whole thing came about as an integrability. So you really need to break integrability and figure out that what happens? Well, let me tell you what this beta ansatz integrability means. It means that when you have three particles coming and scattering off of each other, the order of a scattering doesn't matter. If these three red, blue, green particles come and scatter, if a scattering event 1 happens, then followed by 2, then followed by 3, it gives you the same result if the order of a scattering was different. This is extremely fine-tuned case, and it's very easy to break it. So essentially, this integrability is really not a typical thing that would happen to Hamiltonian, and is coming as a result of fine-tuning, and in fact, is a set of measure 0 if you consider all randomly written, essentially interacting systems. So just to be sure, we don't have shortage of metaphors, is like you have a Achilles heels that's the only, the whole body of the person is vulnerable, and you don't need to be a naughty experimentalist to break integrability. It's more natural to break it rather than not to break it. So how can we break it? One way of breaking it is to couple it to quasi 2-dimension, going second dimension. So you introduce a coupling to this to outside the 2D ring. You get a 14 qubit, and you start coupling it to 7 others that are outside the ring, and you do quasi 2D. So the spectroscopy I show become relevant in here. The bands that we see for 3 excitations overlap with the continuum. So you ask any self-respecting theorist what would happen, they would say that Fermi-Golden rule immediately is going to decay according to Fermi-Golden rule and is going to go to continuum very rapidly. There you go. You take a note of what they say and you go to do the experiment. The vertical axis is if the bound states stay together, the robustness of it, and the horizontal axis is a function of time. For very weak perturbation or no perturbation, this is meant to be flat. That's what the dephasing I showed you. And for very, very strong perturbations, the bound states immediately go away. But for perturbations as strong as the one that generate dynamic in the ring, you can see that the bands does not go away easily. So let me show you further data. Now we do perturbation very, very systematically, and you can see that the rate that the bands goes away, the 3 bound states goes away, is actually very slow. Let me show a cut through the same data as a function of the perturbation, the swap angle going quasi 2D. You can see for a very substantial size of angles, the bands are together. So that's a vertical axis. It's just 2 cuts on the same plot. You can look at the same picture in the momentum space. That's why we did the momentum picture. And you can see that, again, the same physics happens. So the bands stay flat for a very sizable times. And then after that, which is very, very distinct or different from what you would have predicted using simple Fermi-Golden rule. So we did our best. We say that, hey, look, let's just think about possible mechanisms that could lead to this. We came up with a couple of suggestions. All this physics of pre-thermalizations and whatnot is coming from considering very weak perturbation, which is not the case in here, that the whole point is that the perturbation could be very strong and the bound stays together. This was great. We end up the manuscript by saying that we don't know what's happening. I mean, after we have done all these things, and we ended the manuscript by saying that something is lacking. That's beautiful. So then we went home. About a year later, out of clear blue sky of archive, came these 2 works. Without us even talking to them, they start to explaining what this physics is. First, they confirm that the physics that we found, they say that in the limit that Google processor work, that's correct. Then they try to go to the thermodynamics limit, and that was the fun begin because they disagree with each other. And that's really great because that's what I meant by discover it, meaning that we inspire these theory teams to think about what we come up first. Of course, in the limit that we work is all manageable by them very easily, but we brought this problem to attention. And that's our claim to fame. So without further ado, let me get to the second experiment, which is about universality class in the same Heisenberg chain again, and which there has been a prediction for it. So for this, to explain this physics, I need to say a little bit about what KPZ universality class is. So let me explain the KPZ equation. This is the simplest modification to a diffusion equation by adding a very innocent-looking nonlinear nonlinear terms to the diffusion equation, and this is the stochastic noise. And you can see the physics that comes from this equation in ballistic deposition model. So think about the snow fallings. If it sees some the left or this right, it gets stuck. So there's a conjecture which says that the dynamics that you see here is exactly the same thing as in here. Of course, this is a differential equation we are not solving, but I'm saying that the same physics can be seen in here. It's a conjecture distinct from the conjecture which we are about to discuss. So you can take a snapshot of it, and there's a correlation length, and there's a fluctuation in height and all that. And so this physics has been observed. The physics of KPZ is very successful in describing how interfaces grow, how fires propagate in a forest, and has been also discussed and observed that the spin dynamic follows in certain spin models. Quantum spin chains follows the same universality class. What do I mean by that? If you look at this height, and the derivative of this height profile is the same as magnetization profile. Meaning that if you integrate this, basically look at the height fluctuation at the center at time t, and subtract the two asymptotic value at the end of the chain, that height would be something similar. It would be the same stochastic variable as the transferred magnetization, which I'm about to describe. But then within the KPZ universality class, the experts in the audience know that probably we should consider both of these universality classes, which roughly speaking, they come down to what was the initial condition. If the snow was accumulating on a flat ceiling, it was accumulating on a ceiling with a tilt. And we get to both cases by the end of this talk, hopefully. So here is the experiments that we have done. You get a chain of qubits. And you are choosing a parameter mu. This is a positive number, could be plus infinity, or could be more like 5 or 3 or something. And with that probability, you choose to excite qubits on the left side. And with the same probability, you try to, with the opposite of it, you choose to not excite on the other side. And again, we are going to do the Fouquet version of the XXZ model or Heisenberg model. But the physics which was originally proposed for Heisenberg chain, the Hamiltonian is the same as what we are seeing in here for the Fouquet version of it. And as a function of the cycle, Fouquet cycle, we are going to count how many excitations cross the middle line. On the right side, how many blue points go to the right sides at time t, and you subtract how many blue points were on the right side at time 0, and that's a number. And you repeat the experiment over and over again, and you make a histogram. So, so there is a photon loss again, and you remove that. You can normalize your data again. That's why you have two axes in here. So the count number goes down, but the probability distribution can be done because we are able to get maybe 1 million bit strings, and truth to be told, I think about 0.1% of the bit strings have the correct photon excitations, but you have sizable that you can have a statistical significance. So who was the first who said that this should follow under the KPZ universality class is not clear, but let's say that these authors did extensive numerical work and look at the scaling function, and they realized that it deviates from the Gaussian. When you look at the tail of the distribution of this scaling function, when they have gone many, many orders of magnitude, they saw deviation from the Gaussian distribution and consistency with KPZ, and it led them to propose that the dynamic under this model follows the KPZ universality class. So here's the data you have to take. So again, you choose a mu parameter, and I'm showing snapshots of it to show the difficulty of this experiment. And this mu sets up that what is your initial state. And you evolve it for one cycle, and you take 10,000 screenshots, and I'm showing you one instance of it. And you go longer and longer, and I show you samples of what the bit strings look like. It's not that difficult to analyze this and see what is the transferred magnetization. But the conjecture, unfortunately, happens in this limit. Where the mu goes to 0, you can see initially you cannot even see there is much contrast in here at the time equals to 0. But nevertheless, you have to really go to the finite for very late times and take mu equals to 0 because that's where the conjecture is. And you have to evaluate the conjecture at that limit. So Nevertheless, we were brave enough or maybe ignorant enough to try this. And this is the histogram that follows from this data. And we are going to analyze these histograms very carefully to see if it follows this universality class or not. First, I start by talking about there is a distribution. There is a distribution for which evolves as a function of time, and you can get it for various values of mu. First, we can look at the mean and variance of this distribution, and there has been lots of literature on it. In fact, we can even deviate from delta equals to 1. The conjecture is for delta equals to 1, but we can, for just the sake of showing that we are a member of the club, we can change the value of delta, and we can see that the ballistic, super diffusive, and diffusive that has been observed by many other experiments and numerical work is also something we have seen. So this is fine. And then we can look at the variance. The variance scales super diffusive. And we can even lower the value of mu. As I said, we have to go lower the value of mu. And we don't see much deviation in the variance from super diffusive. That's healthy. So it's all consistent to be in the KPZ universality class. And that's the data that they have led many researchers to conjecture or propose that the dynamic here falls into the KPZ universality class. But again, you get Oracle tells you that you have to go further. Well, we had the distribution, so we are going to study its skewness and excess kurtosis. But what I really want to point out before showing you the data is not only just analyzing it, is just to bringing this concept to attention, that now there is experimental data. When you have a distribution, you can just go higher moments so long as you have a statistical significance. That brings this point to attention that when you're trying to classify a universality class, how many moments of the distribution needs to be analyzed? This is the question rather not explored, right? And as far as I know, and I don't read literature, there is no exception, or there is no case that something works up to 10th moment and then it stopped working. This question hasn't been discussed openly or hasn't been much attention because theoretically it's not very accessible and numerically is very difficult problem to do. So what I'm trying to say, again, in the spirit of that hot air balloon analogy, is that we are bringing this matter to attention regardless of what the result is this concept that we are bringing to attention, which I feel is very significant. So this is a very messy plot. I have to walk you over it very slowly. I'm showing you the value of a skewness as a function of time, number of cycles, and for various values of mu. When mu is very large, you can see that the skewness shoots up and probably is going to saturate to some non-zero values. It's a bit hard to see when the mu parameter gets close to 0, the skewness is not very much getting away from the x-axis. And that's what we need to analyze. We have to see what happens when mu tends to 0, not 0, tends to 0 at very long time. So it's not easy to see if it's going to get to these asymptotic values predicted by the KPZ universality class or not. Luckily, we could find an empirical scaling relation which allows us to collapse this data. Now I'm showing the same data set with this scaling factor. And you can see that the two distinct behaviors that we would care about will fall into two different ends of this in this plot. Well, the taking mu to 0 and time to infinity, these two limits are non-commutative limits. So the order that you take them matters, and I would argue that this is the correct order that you have to take the limits. And you can see in this limit, it's distinct from the two predictions that I mentioned about the KPZ universality class. Okay, so regardless of which universality you want to consider, well, you have to consider the Blake range besides the point. You can see regardless of that, you can argue on that case, but regardless, you can see that without going to literally time infinity, you can be fairly convinced that this is going to be close to 0 and it's not going to come off from 0. You may disagree with me and say that, well, maybe you should take the order differently. Okay, so this data doesn't rule it out, but hey, We can do many different ones. You say, why you chose to walk along this line? You could have done many other lines. Okay, I cannot argue back. But what we could do, we could measure the kurtosis, or rather excess kurtosis. And I'm providing evidence that this also refutes the KPZ universality class. And well, I like you to believe that this is not going to get there regardless of how much weighting. It seems to tend towards zero, at least in the time scales that we have been studying this problem. So nevertheless, there are two other theories, and they were co-authors, and you have to study what they are saying. That one of them is predicting a skewness correctly, and the other one is predicting both values correctly. But these are rather, does not explain the physics, because one of them even is a classical Landau-Lifshitz model. So the question is, can you write these models that have enough parameters that captures the physics? So so again, this manuscript ended by, again, declaring ignorance, that we don't know what is the universality class is, and I really like these kind of endings. Okay, I want to be finishing on time. So the two works that I presented to you is the result of the infrastructure that the Google Quantum AI team put together maybe over the last decade. This is now we are seeing how it's giving us results in this non-equilibrium physics. But more importantly, these works and other works have been done in collaboration with many academic researchers, and we are very thankful for them, and we are very fortunate that we have been collaborated with them over the past decade. Thank you.